Okay, so this is lecture number 32, and we were looking at in the last class we completed this power supply noise in PLL, and where the VCO was the main block which we looked at the supply regulation for the VCO. Okay, so the next thing which has been left so far in integer and PLL or an analog PLL is the loop filter, which I haven't discussed. I just told you that in a loop filter we use resistor and capacitor, but surely there is something more to it. Okay, so the loop filter which we have seen is consists of like one resistor which we need to use for stabilization of the loop, capacitor C1 which we started initially as an integrator, followed by another capacitor to suppress the ripple. So this is ICP and V control. Okay, so the thing is that in current PLLs, all your resist passives, which right now in the PLL are only R and C, they are integrated on chip. Okay, and now when they are integrated on chip, you need to worry about what happens to them. So the thing is, first thing is these R and C both are integrated on chip. So the form factor of this or size of R and C is quite important. Okay, so area of R and C both is R and C both is crucial. Is important for integration. Okay, and then the other thing is that since you are integrating it on chip, you will see the same kind. You will see some kind of variation in what you design. You have already designed. So PVD by process voltage PVD variations for R and C, they actually change the loop dynamics, and so the PVD variations have to be compensated for desired loop dynamics. Okay. So earlier you can say if I want to put a microfarad of capacitor for a very low bandwidth, I can take the pin out of the chip and I can put it off chip, but that is no more the case. You want it to be integrated because taking the pin out and putting is more problematic for high frequency pillars. You will have the bond wires in the path and other. Okay. And surely you do not want to waste one pin just to take the capacitor out. But that has been done, that used to be done long back. Okay, and may still be done for a very low frequency PLL where you want a very low PLL bandwidth. You cannot put that capacitor on chip. You may use still the off chip cap. Okay, but surely that is not which we are looking for. We are looking for the integration on chip. So now this resistor is realized. So I think this is something which you all know. Just for the sake of completion, the resistor of any, so let me say, so I think this part is, might have seen that on silicon, sorry, slightly, okay, something. So now this is the thickness of material, length of the material, and width of the material. Any material which I am talking right now, I'm not commenting on anything. That what this material is. So resistance of any material which has the following dimension is defined as the resistivity times L over A. The units for this is ohm, and rho into L by W into T. okay, which is then later defined, like used in terms of process as, sorry, rho over T by L over W. And this becomes RSH times L over W. Okay, so here rho is resistivity of material, which is often measured in terms of in units omega centimeter. Okay, I think you can see the units match here. And RSH is the most commonly used term for resistance, which is defined as sheet resistivity. Okay, and which is has the units, you can say, ohm per square. Okay, we'll see what the square is. So this square is nothing but, you can see the base of, means rho by T is only, means rho by T is commenting about this dimension and the resistivity of the material. Whereas given you have length of the resistance L and width W, so the dimension includes, so the sorry, this definition includes L over W, which is actually is like how many squares, you can count it in this manner. So how many squares you have in the two dimensions. Okay, that's why it is defined as a omega over square. This is for the definition which is being used in any technology. Okay, so okay, that is just for the definition part. Now look at how do you, when you realize this resistance on chip, what kind of resistivity do you get from the material in silicon? So if you are using any metals, let's say like copper, the resistivity of copper is something as 1.7 into 10 power minus 6 omega centimeter. For aluminium, it is 2.7 into 10 power minus 6. And for N-type silicon, you have something as 0.25 ohm centimeter. And for silicon dioxide, which you normally use for isolation, it is close to, I think, 10 power 14 or something. Okay, so if you want to realize a resistance, any kind of resistance on silicon, what do you think among these you are going to choose? You need some finite resistance. Okay, metal resistance is something which you cannot use, because if you want to, kind of the resistance you want to realize is maybe 1 kilo ohm, 2 kilo ohm, or whatever. Okay, there exist different variants, that N-type silicon, P-type silicon, and many others. But among these, which you are going to use? Like N-type diffuse, N-type poly resistance, you may use it. Okay. So this 0.25 is only N-type polysilicon. There is nothing more done to it. Huh? SiO2 is, the resistivity is too high. Huh? How do I realize this? No, I'm not realizing with silicon dioxide. I'm saying the resistivity of silicon dioxide is so high that you will not be actually using it. So what all materials, what all things you have when you are trying to realize the resistance on silicon? You have metals which you use for connections. You have N-type, P-type silicon, polycrystalline or diffuse or whatever they are. Okay. Then you have, there is another thing, something called as metal silicides, where you have the silicon metal implantation in silicon. Okay. Then you have a silicon dioxide which you use for isolation and others. Now the question is, what do you use to realize a on-chip resistance? And looking at this, you can say that using a P-type or N-type silicon is a good means it will be a good way to realize any finite resistance. Finite controllable resistance in a smaller form factor. Okay, there's a lot of things like controllability also there. Means in N-type silicon, now when I say the resistance process variation is important, if I say it's an N-type silicon, it has a finite resistance. What do you think can change the resistance value? Doping concentration, the doping profile can change the resistance, right? So all this process are going to change of resistance, and I can say that over a process process PVD variations, you can easily have plus minus 20 to 30% of resistor variation. And the plus minus 20 to 30% of resistor variation, if you do not do anything, can change your loop gain, margin, noise performance, everything. It's not only about the noise which is being contributed by the resistor, it is changing the whole loop dynamics and bandwidth, which changes the noise contribution of other blocks in the system. Okay. So this is a passive resistance which once you fabricate, it has a finite resistance, and then depending on the process, it has a variation. Okay, so when you realize this resistance on chip, you have something which is often neglected is, so I realize I'm showing a top view. I also will have a context, which is in order to connect to anything, you will connect through metal. So you have metal contacts in the silicon. So the actual resistance which you are going to realize is total R total is equals to your R. Let's say this is N poly. So R poly plus your 2 times resistance of contacts. And this may not be negligible depending on what your resistance is. Okay. So when your resistance is very, very important, you just take care of the contact resistance also. And since I am talking about the contact resistance, let me tell you a very important part here is, let's say you are making this is slightly off the track, but it is important. Let's say you are making any differential circuit. And in differential circuit, let me just say that I have PMOS and NMOS. So I will lay this PMOS and NMOS, and I will connect it with some, the two metals needs to connect. So I will have a contact from PMOS side. So let's say this is PMOS gate, and this is your, one is source, other is drain. Okay, PMOS. And then I have NMOS here, another source and drain. So let's say I connect these two drains. So in order to connect these two drains, I will have contacts. I'm connecting through metal. I will have contacts on both the sides. And if I'm using this particular circuit as a differential circuit, so similarly I will have on the other another differential block, so which will be another, both same source and drain. Okay, so and I connect that through metal. Now if I change the number of contacts on the two sides, then you will see a different DC operating point. You say I'm having this, even if there is no process variation with the MOSFETs or anything, because you change the number of contacts on one side with respect to the other. So if I make another, if I actually go and put another contact in the path, then I will see a different DC operating point. So do not neglect this contact resistance or anything in your calculation, provided it is important. Means if the contact resistance only 1 or 2 ohm and you want to, you're realizing 100, so like thousands of ohm, then it may not, you may not see the pitch, you may not see it clearly. But for differential circuits, make sure that they are differential in terms of each and everything. Otherwise, you will have asymmetricity. Okay. So other than that, now if you look at the resistance variation, which is RSH into so this is, you want to go it with the L over W. So this what all things can cause the variation in the resistance. So sheet resistance can vary because it is dependent on the doping profile. Doping, so variation in integrated resistors can happen for all the different cases. Doping concentration and profile. Okay, then you can have a different actually annealing techniques when you are etching out and everything, that can also change the resistance. Okay, so these are all due to the process variation. You can have a change in the sheet resistance with what you designed for. Okay, the other ones are actually your if I change W or L, right, then also I can have a variation in the resistance. So now if I, okay, so this is basically, this depends on your accuracy of given technology. It depends on that. Okay, your etch profile or etch rate when you are etching any particular, this mostly you can say they comes in a lithographic. So these are all process things, but what we are concerned is how much can it vary, how is it varying, that's a different case. Okay, these things are responsible for variation in the resistance. So if I want to quantify that variation, delta R over R is delta RSH by RSH plus delta L by L and delta W by W. There's no problem here, right? That what only thing which I am doing is I take delta R by R I do, and that is due to all the variations which can happen. And this variation I am saying can be close to plus minus 20 to 30% depending on sizes which you choose. Okay, now as you go to a finer technology, what changes in this resistance? What changes in the parameters? Pardon? So if I want to realize a certain same length resistor in 250 nanometer technology, same doping concentration and everything, and same in like 28 nanometer technology, same length and width, what changes in the technology, as you pointed, is this part. So as you come down to a lower technology, that means that you can have the more accurate, finer dimensions. So that part you change. Okay, and that if the process as the process matures, you will have a lesser sheet resistance variation in the sheet resistance, like resistivity of the material. So if I want to have lesser variation in the resistance, so let's just pick up one example that, sorry. So the sheet resistivity is the same, and R is equals to 1 kilo ohm in both the cases. Sorry, just take an example. R is equals to 1 kilo ohm, and in one case your L is equals to 1 micrometer, W is 0.2, and in another case L is 10 micrometer and W is 2 micrometer. So the total resistance remains the same in both the cases, but which will have a lesser variation, process variation. So this will have a lesser variation. Okay, means lesser variation. I'm just saying plus minus delta R. Okay, but what's the trade-off? You got some benefit, huh? Okay, I can invest that much area, let's say. So area is surely the problem. What else? Capacitor associated with the resistor. So any resistor which you realize on silicon, you should make sure you know that there is a substrate. So let's say you realize this silicon with using some N poly kind of thing. So you will have no, okay, I'm just saying that you will have some context on both the cases, on both the sides. But this one is N poly crystalline, which you used to realize the resistance. But this resistance comes, your substrate will be grounded in most of the cases. You will have the parasitic capacitance. So if you think that you're only realizing a resistance on silicon without any parasitic capacitance, that is not true. Okay, and where is this resistance important? Okay, again, slightly off the thing because it is about implementation. When you lay out any metal wire for connection, okay, so now this is metal where the resistivity is very low. So the resistance which is coming out to be very low. But again, this has a spreaded resistance and a capacitance network. So if you think that I will increase the metal width to reduce the resistance and lower the resistance drop, the thing is that you are also adding more capacitance on the path. So be careful about when you use it, if the captions whether the captions is important for you or not. Okay. The other, so this is about the process variation, which we say that okay, RSH changes, delta L and delta W changes. The other things which causes the variation in resistance value are temperature and variation in resistance due to temperature and your voltage. So they are mostly in any of the design documents. You will find the variation as R times T is R of T naught into 1 plus temperature coefficient 1 into T minus T naught 10 power minus 6 Tc2 into T minus T naught square 10 power minus 6. Okay, where Tc1 is a linear temperature coefficient in parts per million per degree Celsius, and Tc2 is quadratic temperature coefficient in parts per million per degree Celsius square. So any design document will specify that how much the resistance can vary depending on the temperature. So if you are making any design, you also take care that how much does it vary. Another interesting thing is that though I am saying all the time that this is a passive resistance, it has a voltage dependence. And this voltage dependence, you can say, is because this is N-type silicon or P-type silicon, diffused or crystalline kind of silicon, where things will change depending on the voltages applied across the resistance. So it also has a voltage dependence across the, sorry, so, oh, still writing that, V minus V naught, okay, and VC1 and VC2 are similarly linear and quadratic voltage coefficient. parts per million by voltage and parts per million by voltage square. Okay, so other than the process variations and change in the dimension, your resistance can also vary depending on the temperature and the voltage applied across it. Okay, now let's say if I want, so let's consider one variation, temperature variation, and this TC1 and TC2, they depend on the kind of the resistance. They can be positive, they can be negative, large, small, depending on what kind of resistance is used. So if I want, let's say I have two resistance and I give an option that I have N poly and P poly. I can use either of this. This is R1 and R2, and N poly has a positive temperature coefficient, and may just say N, and P poly has a negative temperature coefficient TC1. If I want a matching between R1 and R2, what should I choose as a material for them? N poly, P poly means I mix match, or pardon? So okay, so using combination of R1. So okay, the one way, okay, let me just, what here you are saying is that in order to have a better, so there are two things which I would say. If I am looking for better matching, right, in that case I use only N poly or only P poly. Okay, and then I will look in between them. I may basically look for which has a smaller area, higher density, or which has more accuracy in those parts. Okay, accuracy, density, I will look for the other parameters. Okay, but if I want, if R1 itself needs to be more accurate with respect to temperature, okay, then what I can do is I make R1 as you suggested, R1 as a combination of R1N and R1P, so that on temperature it is compensated. Means the effective resistance looking in this terminal is a temperature compensated one. Okay. People. So I can use that. So depending on what you need, you can have a different combination. So if you are going to use any kind of resistance in a loop filter, you look for what all kinds of resistance exist. What is the parasitic capacitance for each resistance, because you do not want to add a lot of capacitance. How much is the percentage variation in this particular capacitance across the temperature, voltage which you are going to use. So all those things you look for, and then you go and choose select one. Okay. No, because one is a p-type diffuse, other is n-type diffuse. So the concentration of these two things will differ, can differ. Means their dependence on temperature can differ, right? No, if you are talking of only one single semiconductor, means there is nothing. If you are talking as a like intrinsic semiconductor, that has only one property. But if you are talking of n-type and p-type, and then you may have a polycrystalline or diffused, you may have a different kind of variation. Okay, I am not saying here basically p poly, only p poly has a negative or n poly has a positive. I am just giving an example that if you have a positive and negative, and which I am saying they do exist in the in a any given fabrication technology, then if you have that access, you can utilize that. Okay, the physics behind is it's not, it's like not in this part. Okay, so this is all about the passive resistance which we have seen. The next one is the control of this passive resistances. So means no matter what you do, the resistance whichever you realize will vary by certain percentage plus minus, let's say x, and you need to control it. So what is the way to control a resistance if you do not want to change the loop dynamics for a given frequency? So there are two things. One thing is I want to maintain a certain value. So R, so let me just give you two options. R needs to be fixed in, like, make independent of PVT variations. Okay. Inherently you can't do it, so you have to compensate for the variation. For variation. Okay. And the another case is if I want to change the loop dynamics depending on the frequency which I want. Means if I am operating with a different reference frequency, I may not want to have a same, means I have to change the loop components. Okay, so for wide range PLLs, you actually want to change R. You may want to change R. I'm not saying that you always want to change R. Okay, so if you're using a passive resistance, what can you do to change the resistance value? Pardon? Resistor bank is the easiest one. So you can use a resistor bank to vary R. Okay. But any bank can only give you a certain, it will always limit you in within a certain resolution. Okay. So you can use that. That's not a problem. Okay. There is another way to have a varying resistance by using a switch capacitor thing. We will see that when we look at more in a digital fashion, PLL in more in a digital fashion. Okay, so this is all about the passive resistance. Now, if I want, means again the control is still limited. Once you fabricate it, you have to live with it. Okay, so the next case is for using an active resistor, which we are so fond of using all the time that we can't escape this. So let me say if I'm using an active resistor, which is VB, this is V control, okay, this is C1 and C2, and your charge pump current is coming here. And your effective resistance R is mu Cox W by L into VGS minus VT, okay, N minus VDS. Let's not neglect, you want to use it in the linear form. So if this is the resistance which we are going to use, any limitation on any of the control voltages? Pardon? No, I didn't get it. Okay, so the thing is, we all say this is a non-linear thing, but we know that this PLL is going to oscillate at a given frequency. We know this is going to be this control voltage. We can change. So in a steady state, you know that in a steady state, the current which is going into, ideally the current which is going into the loop filter is on an average 0. Okay. Yeah, that's the more problematic rather than the non-linearity. Means non-linearity exists for sure. So what we need to have is that, so in a steady state, you know there is no current flowing through the resistor. Okay, so VGS, VB minus V control minus Vtn is greater than 0, which implies that you have V control as Vb minus Vtn. So by using this kind of resistance, you went and actually put a limit on V control. Now how much Vb can you increase? That's another one. But by changing Vb, you can do it. But in a given process voltage, in a given technology, you have a maximum voltage which you can use. Given the threshold voltage, you are limited by your control voltage is limited, and if your control voltage is limited, so is the oscillation frequency. Okay, so limit on control voltage actually limits oscillation frequency. Yeah, but it can go only to VDD, right? No, so if okay, let's see that. If VB can go to VDD, you take a 1 volt process, right? For a 1 volt process, your VTH, what technology? 65 nanometers, 300 millivolts minimum. So you are basically 0.7. If you are using a 0.7 volt by with a regulator after the V control to control your oscillation frequency, where your supply is limited by 1 volt, the voltage which is passed on to the regulator is only 0.7. No, sorry, is only oscillator is only 0.7. For a 0.7 voltage in 65 nanometer technology, it will be hard to have an oscillator oscillating more than, I would say, maybe 2 to 3, not 5, it cannot exceed 5 gigahertz, regular low VT devices. So you are limiting that voltage. Now I can always have this voltage conversion to some other conversion and gain and all those I think can do that. Right now this is control, this is talking about limiting the control voltage of the oscillator and limiting the oscillation frequency. Okay. Huh? Right. No. So this resistor is in triode region, right? If some, so yeah, in a steady state, so let's say in a steady state there is some current, means delta, whatever it is, but that will have a VDS very, very low. Means what do we have for a, with respect to VDS, you are, for VDS you are very, very low here, and with respect to VGS, let me say your VGS minus VT is also not exceeding. So let's say this is for VGS, sorry, if I want to draw for okay, this VGS, where I assume that the V control is the same as the V source, sorry, source potential is the same, then this one is VB minus V means VGS minus V control minus VTN, right? Now if there is no, if the current which is flowing through this resistor is actually close to 0, then you are operating in this place with respect to VDS. Pardon? I didn't get that. Okay. No, no, no. It will settle to a value. That is not a, so the settling of the PLL is not a problem to any given frequency. Sorry, to a given frequency. The only thing is how much the control voltage can go. So even let me say, if I am getting your problem right. Even when the VCO output frequency, VCO has a range going from 0.3 volt to 1 volt, linear VCO. But the thing is, this is supplied by V control, right? If V control is getting limited, means that's what I'm saying. I'm not actually giving you any in between translation. That's a different case. Okay. But if the control voltage is getting limited, you are always limited on the other side. So you may not be able. This is the case where your frequency saturates after a certain control voltage. So the negative feedback loop cannot take care of anything. Means how much control voltage can you raise? Means you have to change other parameters to get it the desired frequency. Okay. Plus, then when you are going to use this MOS resistance, you may see some kind of leakage to different nodes, and then you will have additional offset or more ripples in the system. Yeah, so if you use active resistance, you have that tunable property with you, is that you can easily tune it, but it comes with the drawback that you will have more leakage and you may have a limited control range, whereas using a passive resistor doesn't give you any such kind of problem. The only problem is the controllability. Okay, so that is the part of the resistor, passive resistor, which you realize. The next one is a passive capacitor. And how do you realize in a given technology? So let me just, so that is realized with the two metal plates. It's a parallel. So there are two ways you can realize. The first one is a parallel plate capacitor. Everyone knows this from long exposure to electrical engineering. So the parallel plate capacitor, you have one bottom plate and then you have another top plate. Okay, and you need to take context from both the plates. So let me just say that I take a context. Okay, so yeah, I take a contact here and I take a contact from here. So these are the two plates, and in between you actually have oxide. So if I give you a side view of this, top metal followed by an oxide, bottom metal. So let's say this is M3. Okay, now what is M3 and M2? I'll just tell you. And then you have maybe a thicker oxide and a substrate. Now thick and thin oxide, that all depends. So this one is thin oxide, this one is thick oxide. Okay, so what these metal M1 and M2 in a given technology, you have a substrate. Okay, and then this M1, M2 are metal layers. It depends how many metal layers do you have in a given technology. And all these metal layers are separated by the insulator with respect to each other. They're not hanging on the silicon, but they are separated by oxides. Now, this using a top plate, what it leads to, so M3 and M2 are the two metals. Okay, so if this is, let's say, the length, and the other side is the width. So the capacitor which ideally you may realize is, do you remember the formula? Epsilon A by D, right? And D is the thickness of the oxide. So if you want to have a larger capacitance in a smaller area, you need to have a thinner oxide, effectively, right? And can you have now, I think in 65 nanometer technology, you have some layer in between the two metal layers to realize the capacitance. I think if you look at MIMCAP, that part, to increase the, so these metal layers come up like not come up. These metal layers are designed for all the contacts and other things. But if I want to have a better capacitance then what the thickness is provided by these metal layers, I need to have something in. Means I need to reduce the oxide thickness, and I can't reduce the oxide thickness with these metal layers. They are fixed. So actually, for MIMCAP, or I will check it again. For MIMCAP, I think you have some layer in between the two metal layers. That is M5 and M6. There is another layer called QBI, if you remember. So there you can only do it that way to reduce the metal capacitance. Okay. Now, so this is the capacitance which I actually wanted. V top and V bottom. What does come up together with this? Bottom plate. And what not about the top plate? Why not? Top plate also. So you get, so you have a desired capacitance which is V top and V bottom. Okay. And then on that you have a capacitance with respect to substrate. Let me just say C parasitic bottom. And you will also have with this from the top layer also with respect to substrate. CP top. This is C desired. So any capacitance comes with this kind of parasitics. Okay. So now if you are realizing a loop filter which captures C desired, you also check out what are the other things which are coming in addition to it. Okay. Now the other capacitance, this is the parallel plate capacitance, is which you can realize using the fringe capacitance. So let me show how you can do it. That I can use, let me okay, this is one. Then I have that, and I can say, let's say both are M3. I can do that. So this is the capacitance which is coming because of the fringe capacitance in the same layer. So you have effectively the capacitance which I am having is this. And this actually now depends on the thickness of the metal which is being there. So any metal layer is not actually a zero thickness layer. Any metal layer which you will have in a given process will have a certain thickness. And the capacitance which you will get here from this kind of fringe capacitance will actually depend on the thickness. Why? Because think about it. Let me show you one. Okay. So, sorry. Consider the view in 3D, then I think you may get that. So let's say this is one metal part, right? And this particular part, let's say, is facing now these are the two, right? So the dimension here are, let's say, X and Y. Now the two faces of these metals which are facing each other are this one and this one, right? So the capacitance is realized between these two faces, depending on the thickness. So if you just place two metals to each with respect to each other, only one parallel line, you have a coupling capacitance, right? Which you always see, Cc. Where does that Cc come from? If the two metals are on the same means if the two metal lines are the same metal lines on the same at the same level, how can you have a coupling Means how can you have a capacitance between two signals which are running on the parallel wires at the same level in the given silicon technology? You can only have when they couple with each other, right, at the same level. And the coupling depends on the area which they are having, which is actually your T times, sorry, which is your T times the length. So if the T reduces to 0, then you will not have any coupling capacitance between the two metal plates at the same level. So using this, you can realize the capacitance, which can be much more denser also at the same level. So what you can means we also do it is that you can have, let's say this is M3 and okay, so this you see as a fringe capacitance at the same level M3. I can have at top of that M4, right? And I can have on M4, and then I can combine M4 and M3 and have more between the parallel plate capacitance also. So let me just see if I can. Fringe capacitance. It comes to, sorry, it comes to the fringe capacitance. It is you can say this is a flux one electrical. This, but this is not. This is, I think this is not provided by the technology quite often. This is what you can create it, and because you have all access to the metal layers. I don't remember whether that is related to the electrical flux or not, but might be the same. Because what you see is the electrical fields lines are confined between two plates facing each other. So in the top one, in the previous one, the plates are facing means as per uh, as per this metal lines going from top to bottom, you can see the two metal plates are facing in a top to bottom approach. Means that way. In this case, they are facing like opposite to each, like it's not top to bottom, but is left to right, or whichever way you want. Okay, that's the only difference. And this kind of capstans, okay, we can use it here, but this kind of capstans can also be used if you want to increase the decoupling cap in your chip. So what, okay, today we are going quite off the track, is if I want to realize a decoupling cap, quite often you use a MOS capstans, right, which has a higher density. I have a MOS, whatever, I actually short both the drain and source. So these drain and source are shorted, and then you have a gate, and you realize between gate and ground, right? Now on top of this MOS, where all the connections are limited to M1, you can place this fringe capstans on top of it. Okay, and then you can have M2, M3, M4, M5 till whatever metal you want to use. So if you go like from M2 to M7 or something, you can increase the density by 50%. Normally for MOS capstans, the density turns out to be at 1 volt is something as 10 or 11 femtofarad per micrometer square. But you can increase that to like 17 microfarad per meter square if you can do that. So I think let's stop here. We'll continue. Yeah. Yeah. Pardon? Okay, so let's see that if you switch it, what happens? That will have other problems. Huh? No, but then how are we having the capstans voltage does not change? Now you can do that. Bottom plate capstans will come. That will have another leakage, right? So let me just say this way. Let's say you are doing this, right? So in a steady state, we know that this will be some voltage. No, you cannot have some voltage. This is going to be zero. Yeah. So this is going to be 0. No, only thing I am saying is any subthreshold conduction is going to change this current. Let's see that, no? Means if you are looking for this node is open in both the cases. So in which case am I going to lose the charge? More. In both the cases, source voltage is same as drain voltage. That is not the one. No. Okay, let's say so this is so what happens happening here is your subthreshold conduction will be basically coming on this V control node. Huh? Yeah, now tell. Go ahead. Yeah. It may end up having the same delta V control in both the cases. That is, but this will surely come with some disadvantage. Yeah. So no, I think effectively if you replace, if you are looking at V control and you replace this with the same model with the same. So what we are saying is, I am trying to replace this with some delta I current. Let's say you replace both or in both the cases with some delta I current. You know, so there in the VB in both the cases will not be the same, right? Okay, so let's see the drawbacks for this. There are drawbacks for this also. Nothing comes for free as usual. Okay, let's stop here.